Howdy, howdy. This is Mr. Potter. What we're going to be talking about for the next couple of sections is the other main purpose of knowing derivatives. We've already talked about it from a graphing standpoint, how to understand the behavior of a graph of a function by looking at where it's increasing or decreasing, looking where critical points are, looking where the function is concave up or concave down, and looking at points of inflection. But the other thing that we look at are optimization problems, because oftentimes in a business sense or in some other sense, we're going to want to find out when the maximum of something is or when the minimum of something is. And what we're going to be talking about is how to take a word problem or how to take a situation and transform it into a mathematical problem that we can solve using the calculus. So here are our keys for optimization problems. The first thing that we have to do is we have to try and identify what it is that we're trying to optimize. Now, often this function that we're trying to optimize is going to be a function of more than one variable. It's going to be some type of relation. What we have to determine first is, are we trying to maximize? Are we trying to minimize? What exactly are we looking for here? The second thing that we're going to have to do is we're going to have to identify the restrictions, because we live in the real world, and so we need real world restrictions, real world expectations. And it's these restrictions that are going to allow us to rewrite this optimization function in terms of one variable. The whole idea is that I want to transform this from a relation to a function, and I'm going to be using the restriction to do this. And once I actually have a function of one independent variable, be it x or t or what have you, then we're going to take the derivative, find critical points, look for where we're increasing or decreasing, or use the second derivative test for concavity to see if we have a maximum or a minimum. And then, of course, the last thing we have to ask ourselves is, do the critical points solve the problem? Because sometimes the critical points aren't going to be the solution. The boundary parts of our restriction are actually going to be the solution. And so this is what we're going to do. We're going to go through about 3 examples here. We're going to start off with some very general mathematical examples, and we're going to go towards more real-world type examples. So the first thing I want to start off with is something very simple. The first thing that I need to do is I need to find out what is the function that I'm trying to optimize. So I'm looking at this. I'm supposed to find the largest product of 2 integers. And so if I want to find a largest product, I'm going to write this relation depending on 2 independent variables where x and y are my independent variables. I want the largest product, so that's going to be x times y. That's step 1. Remember, step 1 was we had to find this, what is it that we're trying to optimize? We're trying to optimize a product. We're trying to find the largest product. Step 2 says that we're supposed to take our restriction. So what is the restriction we have here? Our restriction is that these numbers have to add up to 20. So in other words, I need that x plus y must be 20. That's my restriction. So I'm trying to determine, subject to this restriction, what the largest product is that I could find. The third thing that I'm going to look at is I'm going to look at how can I use the restriction to rewrite this, instead of a relation of x and y, to just being one function, having one independent variable. And we're used to x being our independent variable, so I really want this to be just a function of x, which means I need to find some way to get rid of this y. Well, I know that y equals 20 minus x, so I could replace y with the expression 20 minus x. And so this is step 3. This is what I'm actually trying to find the maximum of. And I'm trying to find the maximum of this function because it's the product subject to the restrictions. So now what I need to do is I need to find critical points. I know that extrema occur at critical points. I also know extrema occur at boundary points. And really, for my boundary points, if x equals 0, then y equals 20. And I'm going to have a 0 product. Similarly, if y equals 0, then x equals 20. So I'm going to have a 0 product. So I really am dealing with a domain from 0 to 20 for my x. X is going to lie somewhere in that domain. What I want to do is I want to find a critical point for here. So I know that p of x is really 20x minus x squared, and I'm looking for a critical point That's where the derivative is 0 or undefined. My derivative here is 20 minus 2x. And polynomials aren't undefined, so I'm just going to set it equal to 0. And I end up with x equals 10 as a solution. So I've found my critical point. And I've also got my domain here. So what I need to do now is to determine, okay, is this really a maximum? And remember that there's two ways that I can do this. One way that I can do this is I can look at my derivative for values between 0 and 10 and values between 10 and 20. And if I show that I'm increasing and then decreasing, then this has to be a relative max. If I show that I've got decreasing then increasing, then this has to be a relative min. So if I choose any value less than 10, say 1, I'm going to get 20 minus 2, which is 18. So my derivative is positive, which means that f is increasing from 0 to 10. And similarly, if I was to choose another number like 15, I get 20 minus 30, which is negative 10. So my derivative is negative, so that means that f is decreasing from 10 to 20. So because I'm going from increasing to decreasing, I know that I've got a local max. Now, let's say I didn't want to use the first derivative, I could also use the second derivative test. Remember that if I can show that I'm concave down at a critical point, then this has to be a local max. And if I'm concave up at a critical point, then this has to be a local min. So looking at my derivative, my second derivative is negative 2, which certainly is less than 0, which means that my function is concave down. And because we're concave down, that means that this is a local maximum. I can use either of these tests, and it basically depends on if it's easier for me to take the derivative once and substitute twice, or to take the derivative twice and substitute once. In any case, though, I know that x equals 10 will yield the largest product. So I've used step 5. I've used the first derivative test, the second derivative test, whatever test I need to find my extreme value. I found the value of x that will give me the extreme value, but now I have to make sure that I answer the question. The question here is really asking me to find the largest product. So I'm really looking for this. And if x equals 10, my product at 10 would be equal to 10 times 20 minus 10, which would be 100. So this is the largest product. So, again, I'm going through a pattern here. This is a very set procedure that's going to help me to solve these optimization problems. First, I have to ask myself, what was it that I was trying to optimize? And this is what I was trying to optimize, the product of two numbers. And the second thing I have to ask is, what is my restriction? My restriction was those numbers had to add up to 20. The third thing that I did is I had to get this in terms of one variable so that I could find critical points. Once I found my critical point, I needed to determine if I was dealing with an extrema, a max or a min. And when we found out that by doing the first derivative test or the second derivative test, that my critical point indeed gives me the largest product. And then once I know it's the largest product, I actually have to answer the question. And my question here is, what is that largest product? It's not enough for me just to find x. I actually have to answer the question. So there's a difference between the solution and the answer. Our second problem is one of the traditional calculus problems. What I'm going to do is I'm going to take a sheet of 8.5 by 11 inch paper. And I'm going to take the corners. I'm going to cut off an x by x square from each of these corners, and that's going to make this kind of cross-shaped piece of paper. And if I end up folding along these edges, what I'll find is that I end up with a open top box. And so my objective here is I want to find the largest volume. So I need to take a look at this from a geometry standpoint. I know that the volume of a rectangular prism would be length times width times height. Or sometimes you'll see that written as base times height. Either one of these is going to help, but this is step one. Step one is trying to identify what is it that I'm trying to optimize. In this case, I'm looking for the largest volume. The second thing is, what restrictions am I dealing with? And there's a rather large restriction that I've got here. The paper in and of itself is 8.5 inches by 11 inches. And so that's the restriction that I've got here. What I have to do is I have to figure out what's happening with my box here. So if I was to cut out an x by x square in each of these corners, I'm going to be taking away from this base here. This base is no longer going to be 11 inches. It's actually going to be 11 minus 2x. So this is the length, and this width is similar, going to be 8.5 minus 2x. So using this restriction that basically the length and the width have to be less than 8.5 and 11 inches respectively, I also have a restriction on this x. Because, of course, if I let x be 0, then I'm going to have a box with 0 height. But if I let x be 4.25, then these edges will touch, and I'll actually end up having a width of 0. So my x value has to lie between 0 and 4.25 inches. That's my domain restriction. That's the restriction that I've got, but I've also, because I have this 8.5 by 11 inch restriction, that's going to help me to get my volume as a function of x, the height of the box. So I'm going to have my length, which is 8.5 minus 2x, times my width, which is 11 minus 2x, times the height, which would be x. So this is my volume. What I need to do now is I need to expand this. So 8.5 times 11. So 8.5 times 11, that's going to be 93.9.35. And then I've got 22 and 17. So 22 and 17 is 39x. And then I've got 2x times 2x is 4x squared. But since I'm multiplying by x, that's really 4x cubed, 39x squared, and 93.5x. So this is my volume. And what I need to do is I need to take the derivative of this. So the derivative of this ends up being 93.5 minus 78x plus 12x squared. And of course, because I'm looking for critical points, I want to take this derivative and set it equal to 0. So I've achieved step 3, where I ended up with a function in terms of one independent variable. And I'm doing step 4. I'm taking the derivative and setting it equal to 0 because I'm looking for critical points. Now, when I've done this using a graphing solver, I found 2 critical points. I found x equals 1.585, and I found x equals 4.915. And I think you see a glaring error here. The thing is, this critical point actually is not within my domain. Remember that my x value must lie between 0 and 4.25. So what I'm really interested in is the behavior of my first derivative from 0 to this 1.585, and from 1.585 to 4.25. And remember, I'm looking for a largest volume. I really hope that I get increasing and decreasing. And so what I'm going to do is I'm going to substitute a value. Actually, you know what? First derivative doesn't seem that nice. I think I'm going to go with the second derivative. The second derivative would be negative 78 plus 24x. And so if I take this value and try and substitute it in, I'm going to substitute it in, and I notice that this ends up being negative, because I basically got 1.6 times 24. That's going to be a number about 40, and I've got a negative 78. So my second derivative is less than 0, which means we're concave down, which means we have a maximum at 1.585. So the last thing that I need to do here is I need to calculate the volume of this. And if I substitute 1.585 inches into my volume formula, I end up with a volume of 66.148 inches cubed. So this is the volume of the largest box that I can make, given a sheet that's 8.5 by 11 inches and cutting off the squares. So this is one of the classical problems in calculus. This is a problem that virtually every calculus class has to come up with, and I can make different permutations of this. I can say, what happens if I cut off a square and cut off so that I end up with a lid that folds over, or that I end up with a suitcase type shape thing? And all of these can be solved with the same technique, coming up with a formula for volume, coming up with a restriction on those variables, and finding critical points and analyzing them. The thing is, when I am in business, I'm going to want to create a container that uses the smallest amount of material. So let's say that I have 100 square inches of sheet aluminum. I actually want to find the cylinder with the largest volume. So what's going to happen here is I'm going to have a body. This is basically the wall of my cylinder. And then out of another sheet of aluminum, I'm going to have to cut out a circle for the top, and I'm going to have to cut out a circle for the bottom. And the thing is, I want this area to all add up to 100 square inches. But in order to do this, I need to get a cylinder, which has the largest volume. And the formula for the volume of cylinder would be pi times the radius squared times the height. So what I need to do is I need to kind of get all of this in terms of r and h. So this is step one. I've identified the function that I'm trying to maximize. This volume equals pi r squared times height. And step two is I've identified this restriction. This restriction is that I only have 100 square inches of sheet aluminum. And so I need to find the cylinder that has the largest volume based on this restriction. So if I'm making this a cylinder, this is going to be my height, the distance from the top of the cylinder to the bottom of the cylinder. But this has to wrap completely around the circle here. So this is going to be 2 pi r. That's my circumference. And for each of these circles, if this is the radius, that means that this is really 2r. And this is 2r. So each of these squares are 4r squared. But I've got two of them, one for the top and one for the bottom. And so I know that my surface area, which can be no more than 100 square inches, has to be given by this 8r squared plus 2 pi rh. And so this is my restriction. This is what I'm going to have to do something with in order to get this to be one function of one independent variable. And because I've got r's and h's, looking at this equation, I think it's easier to isolate h than it is to isolate r. So what I could do is I could take this 100, I could subtract 8r squared, and then divide by 2 pi r to find h. And so everywhere I see h in my function over here, I could actually make this volume in terms of r be pi times r squared times h. 100 minus 8r squared over 2 pi r. And I see some things that are going to happen that's going to make this a little bit simpler. So I'm not going to have to deal with a quotient rule or even a product rule when I'm done with this. I've got a pi in the denominator and numerator. I've got an r in the denominator and the numerator. And 2 goes into 150 times, and 2 goes into 8 4 times. So what I've really got here is r times 50 and r times 4r squared. And so this is my formula for volume as a function of my independent variable r. I've used the restriction in order to get this to be a function of one variable. And so now, since I want to find the largest volume, I want to find the critical points. Again, because I'm dealing with a polynomial, I'm not going to have a place where it's undefined. I have one glaring domain issue. Of course, my radius has to be bigger than 0, because if my radius is equal to 0, I'm going to run into issues. But really, I could make this radius huge. What happens, though, of course, is the height would have to be relatively small. So in that situation, these two things have to add up to 100. So I end up with 100 divided by 8, which is 12.5. So I do end up with a theoretical maximum radius. But for all practical purposes, I just want to look at this r is greater than 0 situation. I'm looking for a critical point. My derivative is 50 minus 12r squared, and I want to know where it's equal to 0. And when I do this, I'm going to end up with 12r squared equals 50, and so r squared is 50 twelfths, or 25 sixths. And so r is going to be, I'm only going to look at the principal root of 25 sixths, because the negative root is not part of this domain. So my radius is going to be root 25 sixths. And my objective is to determine my volume. I want to know if this is a maximum or a minimum. Heaven forbid if this is a minimum. So I'm going to look at my number line. I've got this derivative function, and I've got the square root of 25 sixths. Now I know that 25 sixths is really like 4.16 repeating. So I could try a value of 4, and I could try a value of 5. Actually, the square root of 4, which is 2, or square root of 9, which is 3. I could test values on either side of this. So if I test 2 in here, I'm going to have 50 minus 48, which is positive. So my derivative is positive, which means f is increasing on this domain from 0 to root 25 sixths. And if I try a value like 3, I'm going to have 9 times 12, which is 108, and 50 minus 108 is negative. So I know that f is decreasing from this root 25 sixths to whatever my end domain point ends up being. So looking at what I've got here, my radius is the square root of 25 sixths. My volume has to be pi times the square root of 25 sixths squared times h. Now remember that h is this. So when I substitute, I'm going to get 25 sixths. I'm going to be multiplying times 8. So this is really 100 minus 100 thirds over 2 pi times r is root 25 sixths. And I see some things happening here. Of course, I see my root 25 sixths divides out here. I see that this pi divides out here. And this 2 really goes into 50 and 50 thirds. So I've got 50 minus 50 thirds, which is 100 thirds, times the square root of 25 sixths. And if I do this on a decimal, And if I do this with the decimal, I get 68.041 cubic inches. So this ends up being the volume of my cylinder. My radius of square root of 25 over 6, this is really 2.401 inches. And my height, when I substitute into this expression over here, my height ends up being 5.198 inches. So I've got a can that can hold 68 cubic inches. Remember that a gallon is about 231, so this really holds about a quart of material. And so this is a real-world practical application. I'm going to have a situation where I'm going to have to hold some amount of material, and I do have a restricted amount of canning material to start off with. And of course, if I'm cutting cylinders, I'm going to have waste, and this waste ends up being considered in this problem because I am not using this. It's used to calculate the square inches of sheet aluminum, but it's definitely not part of my final answer. So we're analyzing real-world practical applications where we actually use calculus in real life. So once again, this is Mr. Potter. Thank you for watching. Have a great day.